Okay, so this last session is fully online. The first talk is misuse-free key recovery and distinguishing attacks against 7-round ASCON. And this is a joint work with Raghavendra Rohit, Kai Hu, Sumanta Sarkar, and Siwei Sun. And Raghav will give the talk.
Thank you, Patrick, for the introduction. Let me start with the motivation of this work. So ASCON is one of the winners of the CSER competition in lightweight applications category. And it is also one of the finalists of the ongoing NIST lightweight cryptography project. Now, if we consider the designer security requirements of nonce respecting setting and data limit of 2 to the power 64 blocks per key, then we find that the best known attacks only reach up to 6 out of 12 rounds of the initialization phase. So in this work, we present the first key recovery attacks and distinguishers for 7-round ASCON AED without violating these two requirements. So let me give a brief overview of the ASCON authenticated encryption, so how it works. So it consists of 4 phases: initialization, associated data processing, encryption, and finalization. During the initialization and finalization phases, the ASCON round function P is used to ASCON round function P with A rounds is used to permute the state, while during associated data encryption, the same round function with B rounds is used. So now there are 2 variants of ASCON, ASCON 128 and ASCON 128. The only difference is in the rate value R and the number of rounds B. So now if we look into the round function P, it consists of 3 steps. So the first is the round constant addition, where an 8-bit round constant is added to the second word of the state. Then we have the nonlinear layer, where 5-bit S-box is applied to the 64 columns. And then there is a linear layer, PL, where the rows are mixed among each other. So for example, this is given on the right side, how the mixing is done. So now let me present one of the key recovery attack from our work. So it is based on the ideas of cube attack. So we start with initial state. We set the cube variables in the word 3, which are shown in green. So there are 64 cube variables, and the other nonce values we set as 0. Now we have the following observation. So now if we look into the state after 7 rounds, and if we look at the superpoly of this 64-dimensional cube, then we can prove that this entirely depends on the equivalent key bits, like K0 plus K64, K1 plus K65, like this. And this observation can be used for lower number of rounds. Now, stress here that this observation was already used by ASCON designers to attack up to 6 rounds, but it was not known how to use this to mount attack on 7 rounds. So basically, like how we can use this observation to recover the superpoly for 7 rounds. So in our work, to recover the superpoly for 7 rounds, we introduced a new technique, which is partial polynomial multiplication. So to give a high-level idea of how this works, so let's consider the algebraic normal form of the first column after round 1. So this looks like this is in this table. Now, let's say we multiply this column with this column, then the algebraic degree is again 1. It never increases. So basically, if we multiply this with any other columns, then there is no increase in the algebraic degree, and they will never contribute to the 64-dimensional cube. So the idea is we only need to look at very specific partial polynomials. So we can reduce this table to something like this. Now we use this technique to recover the superpoly of 7 round in 2 steps. So first, as a first step, we enumerate all 32-dimensional cubes, and we know these 32-dimensional cubes depends on 32 equivalent qubits. We also know the information about their degree, so we compute all their superpolies. Now they are all in partial form. Now we multiply all these 32-dimensional superpolies of these 32-dimensional cubes to recover the super poly of 64-dimensional cube. Now, once the super poly is recovered, since we know this is dependent on 64 equivalent key bits, so we can recover the equivalent key by knowing the value of the cube sum. After recovering the equivalent key bit, we can search for the master key, which has only like 64 bits of entropy. So in terms of attack complexities, we require 2 to the power 64 data, 2 to the power 101 memory, and 2 to the power 123 7-round ASCON calls. And we note that this memory to 101, this is only used once. Let's say we are repeating the experiment again, then we don't need this memory. We only need to store the super polys. Okay, so now we look into our distinguishers. So the idea here is, in the initial state, we set the cube variables in word 3 and word 4 as equal. And then we apply the S-box operation. And then we find that after the S-box operation, word 2 and word 3, they are independent of the nonce variables. So we model this explicit behavior using the 3 subset division property and then compute the upper bounds of the algebraic degree. So we find that after 7 rounds, the maximum algebraic degree is at most 59. So basically we can select any 60 cube variables out of 64, and this will give you a distinguisher. Also, we find another interesting observation here. So after 2 rounds, we find a subset of cubes which are always linear after round 2. So you can select any 5 out of 6, and we can reduce the data complexity for 4 rounds from 2 to the power 7 to 2 to the power 5. Yeah, so to conclude, in this work, we have given the first key recovery attack on 7 rounds without violating the security requirements. We improved the distinguishers for 4, 5, and 6 rounds. And we present the first 7-round distinguishers for ASCON in the AED setting. Yeah, thank you.
Thank you for the talk. Does anyone have a question? Yes?
Is it audible?
Yeah.
Okay.
Yeah. So I mean, possibly it's an question. Can we have a similar analysis with other ciphers like AES or the other ones? What are the challenges you can find?
I think we can do it, but certainly, certainly you need to see like how the algebraic grows, because for AES the S box is degree 7, so we know like there's a rapid increase in the degree. So it could be done, but we are not. You have to look into the structure again.
Okay, and one short question: like, can we reduce the memory further? I mean, what is your observation like if you want to reduce the memory further?
Yeah. So so it's about the memory, right?
Yeah.
Okay, so I think all the memory complexities we have given in this work, they are in the worst cases. So I mean, we consider like that all the monomials happen in the algebraic normal form, but that is not the case. So that can be certainly reduced.
Thank you.
Okay. Does anyone has another question? No. So let's thank the speaker again. So Raghav, you can share your next slide.
Yeah. Just give me 1 second. Yeah. So it's visible now.
Yes. So this paper is diving deep into the weak keys of round-reduced ASCON, and it's a talk by Raghavendra Rohit and Santanu Sarkar, and Raghav will also give the talk.
Thanks again. So the motivation behind this work is to somehow improve the previous attacks which I just given the last talk. So if you see the previous talk, the best key recovery attack can on 7 rounds requires 2 to the 64 data and 2 to the power 123 time. And also the best distinguisher has 2 to the power 60 data complexity. So now the question is, can we go furthermore, or do we have any better key recovery and distinguishers for 7-round ASCON? Yeah, so we answer this question in a positive way here. So for this, we give the first weak key analysis of ASCON. So in this work, we have given several weak key distinguishers, and most importantly, for the first time, we have given the practical distinguishers for 7-round ASCON. And we also gave two key recovery attacks with different complexities. And our our attack 2 requires less than 2 to the power 64 data, which is still like the best till now in terms of data complexity for 7 rounds. So for this talk, I will only focus on like the weak key distinguishers. So let me compare our distinguishers with the existing ones. So for all rounds starting from 5 to 7, we are able to find some set of keys where we can decrease the data complexity drastically. For example, for 5 rounds, the previous was with 2 to the power 16 data. Now we find some set of 2 to the power 11 keys where the data complexity is 2 to the power 9. Same thing for 6 rounds, we decreased from 2 to the power 31 to 2 to the power 17. Now for 7 rounds, we are able to find distinguishers with complexity 2 to the power 33. Although this works for a small fraction of keys, but this is still practical. And also the another distinguisher which requires 2 to the power 46 data. Now let's see how we came up with these distinguishers. So the idea here is to find some conditions on the nonce bits VI and key bits, so that when we compute the algebraic degree in terms of VI, this is very low. So based on the ideas of the previous talk, the first condition they put was like they said VI equals VI plus 64. So in that case, these two words Y2 and Y3, they became independent of the nonce variable, and they computed the algebraic degree, which was 59 after 7 rounds. So now the question is how we can reduce it further. So if we see in round 1, word 2 and word 3, they are independent of the nonce variables. So can we make more words independent of nonce variables, or after round 2, can we make all these quadratic terms linear? So what we do, we can make this word 1 after round 1 independent of the nonce variables. So this can be done by putting some additional constraints on the key bits as follows. So if the index is from 56 to 59, we take the key bit as complement of each other. Otherwise, we take them equal. Now again, we compute the bounds on the algebraic degree. So now here we observe that for 7 rounds, earlier the degree was 59. Now it drastically reduced to 45. So this is still within the practical range. Also, after 2 rounds, we find that there is only one word 3, which contains quadratic terms. So if we put some conditions on this again and linearize it, then we can reduce this degree from 45 to 32 again. So this is what one of the distinguishers. So let me give one example of weak key distinguisher. So we take a indexing set I. So this contains 46 elements, and corresponding to it, we define a set of weak keys. So we set ki equal ki plus 64 if small I lies in big I. So if we compute the number of keys, then this is basically 2 to the power 82. Now for each of these keys, if we set vi equals to vi plus 64, then after 7 rounds we observe the Q-sum, then it is always 0. This is because the algebraic degree after 7 rounds is 45, and here we have 46 dimensional Q. So now this indexing set is just once, so we have to capture all the possible sets. So for that, we introduce the notion of weak key space. So at a high level, or like very informally, this means we define some set of keys, and if we pick any key from that, and corresponding to that key, there should exist a d-dimensional Q for which its degree is at most d-1 after r rounds. So for this, we give several properties of this space in our paper, like Hamming weight, the relationship between d and d+1. And we also gave combinatorial approach to how to find the size of this space. So just to end this talk, I will just focus on what are the number of weak keys for ASCON. So if you see for 5 rounds, we can have d equal 30, we find that almost every key is a weak key because this covers the entire space. The same thing happens for 6 rounds. D equals 24, and we have almost all keys are weak keys. And for 7 rounds, we have around 2 to the power 116 weak keys. And we also find a small subset of this WKR, which for which we can decrease the value of data. So this is from 9 to 33. Yeah, so all the source codes for all our analysis are given here. So if anyone is interested, they can verify our results here. Yeah, thank you very much.
Thank you. Does anyone has a question? No question. No question. Online? Okay, so I have one question.
Yeah.
How would you improve the resistance of ASCON against such weak key attacks?
Okay. So I think one of them could be because it completely depends on the S box, right? So I mean, or basically, if you see, so S box is one thing, and other thing is the place where we are adding the round constant. So let's say if we take that round constants, because there are 4 places where we are adding where we have the conditions on the key bits. So if let's say if these 4 bits are 0 instead of 1, then we can increase the number of weak keys from 2 to the power 116 to 2 to the power 120. So let's say we have more ones in the round constants at the first round only, then this will decrease the number of weak keys.
Okay.
So we have to play with round 1 and round 2 only.
Okay, thank you very much.
Okay, thank you.
Another question? No? So thanks the speaker again.
Thank you.
Now, Kwan, you can share your slides.
Hello.
Hello. Yes.
Hi.
Perfect.
Can you guys hear me?
Yes.
Okay, great.
The next talk is exploring differential-based distinguishers and forgeries for ASCON, and it's a joint work by David Géraud, Thomas Perrin, and Kwan Tan, and Kwan will give the talk.
Okay, thank you for the introduction. So I will move on. Okay, so for the motivation for this work itself, basically we want to find automated methods to actually find differential characteristics for the ASCON AE permutation. And then afterwards, we will use this automated method to actually look for characteristics that are very specific and suitable for the differential-based distinguishers that we're going to have. So this is a brief introduction to ASCON, but I think I will skip this slide because I believe Rohit did a way much better job than what I'm going to do. Yep. Okay, so we'll move on to the search itself. For the method that we have, we basically just write in constraint programming using minizing, and it is a bit-based implementation, so that we can facilitate the interactions between the substitution layer and the linear layer. And one of the benefits of actually using constraint programming is that we can actually write our dedicated search strategies. So for each of our use cases, we can actually write a search strategy to actually speed up the search process. So for the actual search itself, we have a 2-step procedure. The first one is basically just to take a single linear layer for the ASCON, and we try to map what are the good active S-box transitions for a single round. So what we meant by good, basically what we want is that after the transition itself, we don't want the number of active S-boxes to explode. So basically we limit the number of active S-boxes that we have after the transition. So once we have figured out all the possible good S-box patterns, what we do is that we actually encode this particular pattern into the CP program itself. So the CP program will actually check, we will actually look for characteristics that actually satisfy this transition for one of the rounds. So for the rest of this talk, I want to differentiate the permutations for the keyed one and the unkeyed scenario. So for the key permutation itself, the analysis can only start from the first or last round because of the key additions and everything. Whereas on the unkeyed permutation, the analysis can say start in the middle because we don't really have the key to like be there. So basically, once we start in the middle, we can actually control some of the bits to ensure that certain constraints are already satisfied at the start, so as to actually reduce the cost of the distinguisher overall. So for the case of ASCON itself, it's actually an unkeyed permutation, but we can also consider it in terms of a keyed permutation by like just adding keys for each round. So the first distinguisher that we have is actually the limited birthday distinguisher. So basically in this distinguisher, what we are trying to do is that we want to find out the cost of, say, let's say if I have two plain text, x0 and x1, that have a difference in d in, and we want to ask is that like how many pairs we need in order for, let's say if I map them x0 and x1 with the function f, we will get a difference that is in d out. So for the unkeyed permutation, the limited birthday distinguisher, this is actually how we build the distinguisher. So we start off with a differential characteristic, and then we propagate it backwards and forwards with probability 1. And this will give us two sets, d in and d out, for the input and the output. And in some cases, actually, once we propagate, the number of differences in d and d out are actually rather huge. So if it's huge enough, we are unable to actually compute the size, which will lead to see whether the cost of a generic distinguisher is actually larger or smaller for it. So in those cases, we turn to looking at the complement of the sets themselves. So we basically find a lower bound for the sets of the complement, and this will give us an upper bound for the sets d in and d out. And with the upper bounds, we can actually compute the cost of a generic distinguisher, and we compare with the ones that we have and see whether we will get a distinguisher out of it. So the next one is a boomerang distinguisher. Over here, I will just discuss again for the unkeyed permutation case. So basically, for us, we have a 4 and a 5 round boomerang distinguisher. So for the 5 round, basically we use a upper 2 round trail and a lower 3 round trail. And for them, we basically we choose the starting point in the middle such that it's actually close to most of the constraints. For the 4 rounds, we actually start in between the round 2 and round 3, because there are basically 4 active S boxes around. And for the 5 round case, we start off between round 3 and round 4, because there are a lot of constraints at the round 4. So these are the results for the keyed permutation case, arranged in ascending order of complexity. And this is the results for the unkeyed permutation. So basically this case, we can start in the middle. So generally the complexities are way lower. And the next up is the forgery and collision for the ASCON AE. So in these cases, we have to add additional constraints to our CP model. And the reason is because we need differential characteristics that fulfill certain constraints. Because in the case of, for example, in the forgery, we can only interact with, for example, in the case of ASCON 1 to 8, we can only interact with the first 64 bits of the state. Basically, so in order to have a forgery, we have to have the differential characteristic to start with a difference that's in the first 64 bits and end with an output difference that is in the first 64 bits as well. So with that, we also try multiple such strategies because the strategies have to change based on the conditions available. And these are the results that we have for forgery and collision. So in summary, we have used the CP to actually model the ASCON permutation, and it actually performs as well as the dedicated heuristics methods. And next, we also found new distinguishers for the ASCON permutation, and as well as improve some of the existing forgery and collision results for ASCON. Yeah, so that's the end. Thank you very much.
Thank you for the talk. Does anyone have a question? No? Online? No? So why did you choose a CP solver instead of SAT or MILP ones?
Okay, so we choose a CP because mainly because we can actually play around with the search strategy. First of all, actually CP is a very easy program to actually like just encode the entire cipher itself. And the next thing is that they have a wide range of like solvers and search strategies that we can play around with. Whereas in the case of like SAT itself, we are often limited to just a few choices. So yeah, we basically just want to see what's the prowess of the CP when it applies to ASCON.
Okay, so you mean that the search strategy is very important in the speed of your solvers?
So actually in this work itself, we actually tried a lot of different solvers and a lot of search strategies. And actually we find out that actually the search strategies impact the search results very, it's quite essential. Because for certain search strategies, if you don't put it nicely, it will take like a few days to even produce a single result. Yeah.
So what was the best strategy?
I don't really have it with me right now, but I believe it's inside our paper.
Okay. I will read it more carefully. Thank you. Does anyone have another question? No? So thanks the speaker again.
Thank you.
Okay, so the next paper is Bounds for the Security of ASCON Against Linear and Differential Cryptanalysis. It's a joint work with Johannes Erlacher, Florian Mendel, and Maria Echelsider. Okay, and Johannes will give the talk.
Thank you very much for this introduction. So yeah, my name is Johannes Erlacher, and this is a joint work together with Florian Mendel and Maria Echelsider on Bounds for the Security of ASCON Against Linear and Differential Cryptanalysis. So the motivation behind this work comes from the increasing popularity of designs with weak alignments and larger state sizes, like ASCON, for example. For these designs, if we look at linear differential cryptanalysis, we usually see a gap between the provable bounds and the best known characteristics. For the ASCON permutation, for example, we only have bounds up to 3 rounds, but we have found characteristics far beyond that. These bounds are usually proven by means of MILP, SMT, or constrained programming, while we are searching for good characteristics using heuristic search tools. We therefore were interested in using Boolean satisfiability models to prove new bounds for this permutation. We see recent developments in this field, like encoding methods for characteristics proposed by Sun et al. We use these encoding methods to derive linear and differential models of the ASCON permutation, with which we were able to verify existing bounds very efficiently. Unfortunately, though, we're not able to derive new bounds for more rounds in a reasonable runtime using these models. We also see that there are different methods to constrain the maximum weight of S-box transitions within our model. These alternative counter encodings provide optimizations in terms of the number of variables and clauses they are using, and can therefore significantly impact the runtime for certain problem instances. Finally, I also want to mention that there are generalized parallelization approaches utilizing multiple SAT solver instances in parallel to solve a single SAT problem. We looked into some of these approaches as well, but unfortunately did not see any runtime improvements for our specific case. Therefore, we propose a new manual parallelization approach with the goal of proving new bounds for the ASCON permutation. Such an approach requires us to partition the search space into many independent problems, which we can then solve in parallel utilizing multiple solver instances. We chose to categorize characteristics based on a so-called girdle pattern, which we define as the specific S-box activity pattern within the round with the fewest active S-boxes for any given characteristic. We get a partitioning from this idea by fixing a specific girdle pattern in a specific round in our model and repeating this for every possible case. This approach enables us to propose further optimization steps, like considering rotational symmetries within the permutation, and use necklace theory to therefore eliminate redundant checks in our search space. We also consider shared preconditions among our problem instances, which enables us to use models with reduced complexity to pre-filter our partitions. And finally, we can consider pools of similar problems as a single problem instance in order to reduce the overhead this approach has. So with this new approach, we're able to prove two new bounds for the ASCON permutation, and that is that a single characteristic for 4 rounds of ASCON must have at least 36 active S boxes, which was proven in around 600 CPU days, as well as that a single characteristic for 6 rounds of ASCON must have at least 54 active S boxes. This second bound was proven in around 60 CPU days because we were able to utilize intermediate results from our previous 4-round bound. So with these two new results, we can derive 3 interesting bounds for the ASCON family. That is a 6, an 8, and a 12-round bound. If we look at the authenticated encryption scheme, for example, there the initialization and finalization phases both use 12 rounds of the permutation, and there our new 12-round bound, which is almost certainly not tight, already provides an ample security margin for 128-bit security. The 6 and 8 round bounds, on the other hand, are relevant, for example, for the data processing phase of the authenticated encryption. For this 6 round especially, we would like to improve or extend this bound to a probability of 2 to the power of minus 128, if possible, in order to provide an even stronger security argument for schemes using 6 rounds of the permutation. Other potential follow-up work would include applying this approach to other designs sharing a similar structure to ASCON, as well as utilizing the SUT model to potentially evaluate the clustering effect for specific cases or potential dependencies for differential propagations. One more thing I want to mention is that during the RUMP session, Raghavendra Rohit mentioned very interesting results for differential characteristics in ASCON, which might enable us to prove an actual tight bound for the number of active S boxes over 4 rounds. We will definitely have a look at this as well. Thank you very much for this very interesting talk. So to summarize, we propose a manual parallelization approach based on Boolean satisfiability models with which we're able to prove 2 new bounds for the ASCON permutation. These bounds are almost certainly not tight, but they are enough to support trust in this permutation. With this, I want to thank you for your attention, and if we have time and there are any questions, please feel free.
Thank you for the talk. Question?
Hi, Patrick. I have a question. Yeah, so thank you for your talk. So for 4 rounds, you mentioned like you did something around like 600 CPU days. So
yes.
In terms of like the activity patterns, how many cases did you consider?
In total, I think it was 2 to the power of 26 different patterns. Which we had to consider. That excludes, so these are all the rotational invariant patterns, so excluding, so accounting for the rotational symmetries.
Okay. I have one more question. Like you mentioned about Gödel patterns. So how do you ensure that all the Gödel patterns cover like the entire space for your 4 rounds?
How we ensure that. So let me just move back here. The Gödel patterns basically, how do I put this very quickly? They mark the round with the fewest active S boxes, the activity pattern for a characteristic with the fewest active S boxes. And this means that going from fixing this, fixing a specific pattern accounts for all characteristics sharing this specific pattern in this specific round, right? And if we cover all patterns in all rounds, that means we will cover all the potential patterns up to a certain bound, if that makes sense.
Yeah, okay. Yeah, thank you.
Does anyone has another question? No? Okay, so thanks the speaker again.
Thank you.
So the next talk is security of COFB against chosen ciphertext attacks. And the talk is, it's a work from by Mustafa Kairala, and he will give the talk.
Thanks for the introduction. So I will be talking about security of COFB against chosen ciphertext attacks. So COFB was designed by Chakraborty, Veta, Minimatsu, and Nandi in 2017. And it stands for combined feedback, and it is the basis for GIFT-COFB, which is one of the finalists of the current NIST lightweight cryptography project. How COFB works is as in this diagram. So first, it absorbs the nonce and encrypts the nonce with a block cipher call to generate a half-block mask and also the initial state of the encryption. And after that, it absorbs the associated data and the message through a combined feedback function and masks every time before applying the block cipher. And in the case of this talk, we don't really care about the block cipher. Even if the block cipher is replaced with a PRF, the analysis will still work. And few things we will need to observe here is first that the mask we use to mask the state at every time and also the initial state are almost the same. So the mask is just half the initial state. And if we look at the message part, once we have a known message, we can see the outputs of the block cipher here, and the inputs, we can see half the input to the block cipher. So COFB has a birthday bound, but usually schemes that have a birthday bound have a quadratic bound like this, where when the amount of data encrypted is small, it has almost n-bit security, but as the data increases, it reaches birthday bound. While schemes that have a linear bound like this, sigma over 2 to the n over 2, usually have a small tag. COFB has a linear bound like this, but it has an n-bit tag. And there was an attempt in the Journal of Cryptology by the designers to improve this bound to a quadratic bound. So this led to two questions. First, can we break COFB with this many forgeries, the 2 to the n over 2 over n, which is claimed by the designer, without any encryption queries? And can we show that COFB, because it has this linear bound, behaves like a scheme with a shorter tag? And the answer to both questions is yes, but with some caveats. So we can show attacks that work with 2 to the n over 2 forgeries with negligible amount of encryption queries, but there is a logarithmic factor, so it's only 2 to the n over 2, no over n. And we can show that COFB, especially GIFT-COFB, has behavior that looks like a scheme with an n over 2 bit tag. So to show this second question, we need to consider indistinguishability when forgeries are allowed. And here it's a bit of a misuse scenario where we perform encryption like any indistinguishability game, but when we do decryption, we always do the real decryption. So decryption will always perform normal decryption, but we still need to distinguish the encryption from a random oracle. Why we do this? Because there was a generic attack on schemes with short tags proposed on the NIST LWC forum by Alexandre Mej, where the adversary will try to guess a tag corresponding to a fresh nonce. And then once the forgery succeeds, he will be able to observe some information about the key stream of that nonce. At a later stage, if this nonce has not been used before, he will observe a message encrypted by the same nonce and will be able to partially decrypt it. And in this attack, he has not violated the requirements to be nonce respecting. And this attack will depend on the tag size. So if the tag size is short, then the attack will work with low complexity. So we can show a similar attack on COFB, which requires two encryptions. So first, we have a known plaintext query. And as I said earlier, given this known plaintext query, we can observe 2 to the n over 2 candidates to the input and output of the block ciphers. So we can observe the output deterministically, and we can observe the input masked by an n over 2 bit. So we have to guess these bits. So we will guess these unknown bits, and for every time, this will give us a candidate for P and candidate for V, and we can use that as a nonce and then construct a forgery accordingly. And once we have guessed the mask correctly, the forgery will succeed, and we will have a fresh nonce that has not been encrypted before. Once the forgery succeeds, we can then encrypt a message with this fresh nonce with a different message, and we will be able to distinguish it from random bits. So this attack is optimal when the nonce size is n, because we assign p to n, and if n is less than n bits, then we will have problems by doing this assignment, and we will need more encryption queries to satisfy this. And the attack resembles the attack on short tags. It just needs one extra encryption at the beginning. So we do one encryption and then 2 to the n over 2 decryptions and then one encryption. We have also in the paper other forgery attacks on COFB. However, these attacks cannot be translated to indistinguishability, but they can be used to show that the security bound from Journal of Cryptology 2020 is inaccurate. So to sum up, COFB can be forged with 2 to the n over 2 forgery attempts and one encryption. The indistinguishability attack we proposed is optimal when the nonce is n-bit, which is the case for GIFT-COFB. And the tag size of COFB offers little advantage over n over 2 bits. So we can probably safely reduce the tag size to n over 2 bits without changing the security so much. And unfortunately, the attempt to improve the security bound is not correct. An open problem is that we still have the logarithmic factor in the security bound, but in the paper we discuss some reasons why it's probably artificial, but we leave proving this for other works. Thanks for watching, and I would like to thank the reviewers and Titsui Iveta and Kazuhiko Minimatsu and the rest of the GIFT-COFB for comments on this paper. Thanks.
Thank you. Does anyone have a question? No? So we will thank the speaker again and move to the last talk of the session. Okay, so the last talk is linear cryptanalysis of 3 AEADs with GIFT-128 as underlying primitives, and it's a joint work with Lingsong, Wei Wang, Mei-King Wang, and Lingsong will give the talk.
Thank you for the introduction. The name of the talk is Linear Cryptanalysis of 3 AEAD with GIFT-128 as underlying primitives. Linear cryptanalysis is one of the most fundamental methods to evaluate the security of symmetric key primitives. Compared to differential cryptanalysis, we found that linear method is more suitable to the analysis of the AEAD since it works under the non-plain text attack setting, and we will see some AEAD works in nonce-respecting scenario, so we think linear method is more suitable. This paper aims to evaluate the security of some AEAD with the linear method. The contribution can be divided into 4 parts. Firstly, we create specialized set problems for the search of linear distinguishers coordinate with the attack setting. With this method, we improve linear attacks on GIFT-COFB and SUNDAE-GIFT. Thirdly, we propose the first cryptanalytic result on HYENA. Also, we provide improved linear attack on GIFT-128. The first target is GIFT-COFB. Since Mustafa just gave the scheme of COFB, we skip some detail. The EK function in the case of GIFT-COFB are referred to as the cipher GIFT-128. The ciphertext generating phase explores the feedback function G, which is a linear function over the 128-bit input. We target the encryption functions in the message processing phase highlighted in red. The property of the primitive puts some restrictions on the linear approximation in the linear attack. Firstly, since the designers claim 64-bit NDCPA security under the non-respecting scenario, so the data complexity of a valid attack on GIFT-COFB should be lower than 2 to the 64. Secondly, note that the most significant 64 bits of the input for the EK function are masked by the value L, and L depends on the value of N and K, so L is unknown. Therefore, the verification of the linear relation should be irrelevant with the most significant 64 bits. So to accomplish the search of linear approximations fulfilling this restriction, we attempt to encode it with Boolean equations. We create a specialized set problem targeting the conditional linear trail. Given that GIFT-128 achieves full diffusion after 4 rounds, we conjecture the maximum number of rounds appended before the linear distinguisher in the attack on the primitive is 3. Regarding the 3 rounds extended before the linear approximation, we introduce extra variables to locate the bits involved in verifying the linear relation. According to the functionality, the extra Boolean equations in the specialized set problem are divided into 3 parts. The first part identifies the necessary bits for the calculation of the linear relation. The second part ensures the irrelevance with the most significant 64 input bits. The last part connects the extended rounds with the linear trail. After integrating these equations, the specialized set problems can find distinguishers matching the attack setting. We apply the specialized set problem to assist the search of linear distinguishers for GIFT-COFB and utilize the newly identified 10-round linear approximations to realize 16-round key recovery attack. The second target is HYENA. It is the instantiation of hybrid feedback-based encryption with authentication modes of operation with the cipher GIFT-128. We also aim at the encryption function in the message processing phase highlighted in red. Also, there are some restrictions on the linear approximation in the linear attack. Under the non-respecting scenario, the designers claim that for a valid attack, the data requirement should be lower than 2 to the 64, and the time complexity is bounded by 2 to the 128. Beyond that, HYENA also creates a 64-bit unknown value dirt before the associated data processing phase. So the verification of the linear relation should be irrelevant with the least significant 64 bits. To accomplish the search of linear approximations fulfilling these restrictions, we replace the second part of extra Boolean equations in the specialized set problem. With a 10-round distinguisher, we realize a 16-round attack. Then we analyze SUNDAE-GIFT. It is a family of EAD that exploits the scheme SUNDAE with GIFT-128 as the underlying block cipher. Unlike the case in the previous 2 primitives, because there is no limitation at the input of the EK function, they propose to attach 4 rounds and 3 rounds before and after the distinguisher. The 10-round distinguisher is a unique one, achieving the minimum number of guess sub-KBs. And we finally launch a 17-round attack. The last target is GIFT-128. We find the 19-round distinguisher attaining the minimum number of guess sub-KBs and finally launch a 25-round linear attack. So lastly, a brief conclusion. In this work, we firstly create specialized set problems for the search of linear distinguishers coordinate with the attack setting. With this method, we improve linear attacks on GIFT-COFB and SUNDAE-GIFT. We propose the first cryptanalytic result on HYENA. Also, we provide improved linear attacks on GIFT-128. That's all for the presentation. Thank you for your attention.
Thank you. Is there any question? Online? No? So I have one. Do you have any idea to increase the success probability of your attacks?
Sorry, increase what?
The success probability.
Success probability. Okay. I think increase the success probability is very hard because we should find some improved linear distinguishers. However, in our searching phase, we find the distinguisher in the paper is optimal to some degree. So I think it's hard to increase the success probability.
Okay, thank you.
Thank you.
No other question? Okay, so thank the speaker again and all the speakers of this session. And now Christina will give some closing remarks.
Yeah, so hello again. So it's like closing remarks, but I don't have anything special to say. Kevin, would you like to say something?
No, I think not. I think we've had a good conference. I wish I was there.
Thank you very much for your help with all this. And thank you all for being here. And I hope you have a safe trip back home. And hope to see you all next year, hopefully in China. Yeah, so I think we can just stop here.